Hi, my name is Joe Chacon. I'm an electrical engineer with Padge LLC. This is the second of several videos about harmonics. Today, I want to talk about where harmonics come from. They're not some magical thing made by leprechauns. So let's get started. Harmonics are created by connecting to a non-linear load. That's a fancy way of saying your load isn't purely resistive, inductive, or capacitive, or a combination of those. Harmonics have existed in nature probably since creation. Harmonics in an electrical system only became a concern about 110 years ago. Electric arc furnaces seem to be one of the biggest harmonic generation components by the 1930s and 1940s. So this phenomenon is not new. I want to look at one of the more ubiquitous harmonic generation components in our time. That is the 6-pulse rectifier. They're cheap and very common. They're used on the front end of many devices like variable frequency drives, or even used by themselves as a standalone device. This is what a typical circuit looks like. Let's assume our input voltage is 480 volts AC and the load is 2.13 ohms. These 6 diodes will chop up the AC signal into 6 distinct pulses that is close to DC, but not quite. The waveform on the DC ends up looking like this. I've shown this plot with ripple and the plot with RMS. By ripple, I don't mean the cheap one popular in the 1970s. I mean the 6 pulses you see bouncing between 588 volts and 678 volts. For all practical purposes, this is DC. Now, when the load is applied across the rectifier, we get this plot. By the way, I'm making all these plots in Excel. I'm doing that to show you don't need MATLAB, Python, ChatGPT, or DeepSeek to do the math. This video is about the line side harmonics created by the load. So far, we've only been looking at the load. Let's look at the line side now. For all practical purposes, a diode only lets current flow in one direction. We say when current is flowing, the diode is conducting. In our example, our first conduction interval lasts from 0 degrees to 60 degrees. For 60 hertz, this is exactly 2 7/9 milliseconds. The voltage applied across the load is our VAB, 480 volt line voltage. The magnitude of the A phase line current is the same as the B phase line current. It goes through diode D1 to the load and then through diode D6. I'm going to draw a line through our example schematic to show the conduction path for the first interval of 60 degrees or 2 7/9 milliseconds. This chart shows all 6 conduction intervals. I'm not going to draw the other 5 on the schematic because I hope it is clear. The next part can be extremely difficult to show the chopped up waveforms on the AC side. I debated whether to show the full derivation and have decided not to. Some of you are probably excited, and some of you are probably annoyed. I'm not diving deeper. If you're annoyed, the math is called Fourier series. Excel can do it, and a lot of other higher-end computational software packages can also do it. The idea is to compute the Fourier coefficients for the harmonics being analyzed. I did this and came up with these coefficients. I also did this for the fundamental and came up with 0.5513. The last thing to do is normalize the Fourier coefficients to the fundamental. This just means the dividing the coefficient under consideration by the fundamental coefficient. So the normalized coefficient for the fifth harmonic is negative 0.1103 divided by 0.5513, which is negative 0.2001. We only care about the magnitude, so the negative goes away. This is a summary of the normalized coefficients for our example. Normalized fifth is 20.01%. Normalized seventh is 14.29%. Normalized 11th is 9.09%. I put these values as multipliers to my fundamental in Excel, and this is what phase A voltage would look like when referenced to neutral or ground for this load. It looks kind of gnarly, huh? I hope it is a bit clearer as to how harmonics can be created upstream because of a nonlinear load such as a 6-pulse rectifier. The next videos will look at what harmonics do to a conductor and then what they do to a transformer. I hope this knowledge can help you become the harmonics guru in your company. Please look us up at padge.org. That's padge.org if you need anything on this topic or others.